momentum. So our first lesson, our first starter, is going to be basically thinking about what actually is momentum. It's something that you hear quite often in, like as a figure of speech. People often say, oh, you didn't have the momentum to do that. I mean, it's one of those things that in physics we've got a really specific definition of it. It's linked to all of those things, but what we really need to do in this sort of series of lessons is make sure that we've got our definition for momentum really tight and that we can calculate it basically. So, this lesson, number 1, momentum and impulse. Momentum you will probably have heard of before, it was on GCSE spec, and as I say, a figure of speech. Impulse you probably won't have heard about in physics, but isn't a very complicated concept. The topic's then going on to think about impact forces, conservation of momentum, including what elastic and inelastic collisions are, and explosions. So, lesson 1, momentum and impulse. Our spec reference is this section on momentum. We need to know what it is, we need to know conservation of it, we need to do some quantitative examples in one dimension, we need to know Newton's second law, stated as F is rate of change of momentum, we need to know what impulse is, we need to know what a force time graph is, and some more questions about stuff later on, like impact forces, elastic and inelastic collisions, and explosions, and application of it. So, fairly straightforward. We'll run through it this week. This lesson, we want to calculate momentum, maybe describe the link between Newton's laws of motion and momentum, and define the impulse of a force, and calculate it from a force time graph. So, what is momentum? Well, that's a difficult question, isn't it? If we were talking in physics speak, we would say the momentum of an object is defined as its mass multiplied by its velocity. In symbols, we'd say P equals m times v, P equals mv. Does that tell you anything about what momentum is? Because I have to say it doesn't tell me anything. It tells me the useful physics thing, P equals mv. It doesn't tell me what momentum is as like a quality. That's quite hard, describing what momentum is. It's really something like the tendency of objects to keep moving when they are moving. Sort of. It's a vector quantity. Its direction is the same as the velocity. So whatever direction the object's moving in, that's the direction that its momentum's in. So it's going to keep moving in that direction unless there's a force on it. And that's our link there to Newton's laws, isn't it? That we need a force to make something change its velocity, change its momentum in this case. If its momentum is bigger mass or bigger velocity, we're going to need a bigger force to make it change. Via Newton's second law, force is mass times acceleration. If we want its speed to change, acceleration, we need a bigger force. If we need a bigger mass to change, we're going to need a bigger force. If the mass is measured in kilograms and velocity in meters per second, then the units of momentum are kilogram meters per second. Smoosh the two together. So, for example, we found these two momentums. A cricket ball, mass 420 grams, thrown at 20 meters per second, and B, a steamroller of mass 6 tons, moving at 0.4 meters per second. Now, I just want you to have a think beforehand. Which of those two things do you expect to have a bigger momentum? Will it be the cricket ball or will it be the steamroller? Think about why that is in your head. So, part A, we're saying momentum is mass times velocity written in words. So we substitute in. Except, what have we done? 420 grams needs converting into kilograms. We need to be working in the SI units. 420 divided by 1000 is 0.420 kilograms times by 20 meters per second, which gives us 8.4 kilogram meters per second. Part B, the steamroller, if I write this one in symbols, P equals m times v. I substitute in, P equals 6 tons converted into kilograms, 6 times by 1000 is 6000 times by 0.4. Working that out gives us P equals 2400 kilogram meters per second. Does that match up with what you expected beforehand, of which one would have the bigger momentum, the cricket ball or the steamroller? It's quite clear that the steamroller has a much bigger momentum than the cricket ball. Why is that? It's 6 tons instead of 420 grams. A good way to think about which one has the most momentum is what is going to happen in a collision between those two objects. So if I throw a cricket ball at a steamroller, which one of them is going to come out on top? I mean, it's a bit clear in this example, but imagine you're walking down the corridor at school and there's some year 7s. Which one of you two is going to come out on top? Well, the year 7's probably really tiny, isn't he? So the year 7's going to get bumped away, and then you guys are just going to keep going with what you're doing. You would have the big momentum because you are larger than the year 7. Newton was the first person to realise that the effect of a force depends on both its mass and the amount of force. And he published that, his Laws of Motion, in 1687, in that book there, the Principia Mathematica. Even though it was published in the 17th century, it's still useful today. I mean, we'll launch rockets to the moon or into space using them. They're as accurate as they need to be for most things, except atomic scales. We can't use Newton's laws at atomic scales. We need quantum mechanics instead. We can't use them when we're travelling close to the speed of light, because we need special relativity then for high speeds. And we can't use it in particularly strong gravitational fields. That is where general relativity applies. So really in both cases we need Einstein's theories of relativity. Despite the limitations, each of those models, quantum mechanics and special and general relativity, can be shown to simplify into Newton's laws. Impulse, the one that you wouldn't have heard of, it is defined as the force multiplied by the time for which the force acts. So impulse is force times by time, or impulse is F delta t, as in force times change in time. The units of impulse are Newton seconds, Newton's ns. Force times time, Newton's seconds, Newton seconds. As a bit of an aside, if impulse is F delta t, we also know that Newton's second law is F equals ma. So we know that impulse has got to be, substituting in, mat, mass times acceleration times time. If we use the no s equation, v equals u plus at, and rearrange it for at, we get v minus u. So if I substitute that at into the impulse formula above, I get impulse equals m brackets v minus u. Multiplying out those brackets gives me mv minus mu. Well, that's mass times final velocity minus mass times initial velocity. But mass times velocity is momentum, so that's going to give us the final momentum minus the initial momentum, p2 minus p1, or impulse is delta p. There's two things that are important here, and those are our two formulas, two definitions. One, the definition, so the impulse of a force acting on an object is equal to the change in momentum. That's an important thing. We're saying that, yeah, if that's the case, change in momentum, well, units of that then could be kilogram meters per second. So we've got two alternatives for units of impulse, Newton seconds or kilogram meters per second. Both of them are correct because they're interchangeable. Our two important things then are impulse is force times time. That's our definition for what impulse is. Second important thing is that impulse is the change in momentum of that object. So impulse is force times time, and impulse is also the change in momentum. We can plot a force time graph. Guess what that is? It's a graph of force against time. This one is quite boring. The force is constant from 0 to time t and then stops. You could have a more interesting force, but I'm not going to show you it because we don't need to. So the area underneath that graph, it says on there, but I'm going to say the area beneath the line represents the change in momentum or the impulse of the force. If I find the area underneath that particular one, I do F times by T. Well, Ft is the change in momentum or the impulse. So you need to know from the spec that this is a force time graph and the area beneath it represents the change in momentum or impulse. So finally, what is the difference between impulse and change in momentum? Hopefully we realise there is no difference. They are the same thing. Impulse equals change in momentum. It's like when we talk about energy and work. Energy and work are the same thing, measured in the same units, with different names depending on what we're talking about, just because physics likes to confuse you sometimes. So this lesson, what do we need to be able to do? Calculate momentum, calculate impulse. So the questions underneath are going to be about calculating momentum and calculating impulse.